So, okay, so we're going to look at something called PID control. Actually, we'll leave out the I for now. Okay, so we're going to look at PD control for mass spring damper. Okay, and then we'll use that as a basis for independent joint control. All right, so let's, here's the picture. Here's a mass. And here is a spring. And the spring is attached to a wall. Okay, and let's say the spring constant is K. This displacement is X. Okay. All right, and so if I want to write the dynamic equations, it would be, okay, so let's just assume the mass is equal to 1 for convenience. Okay. The dynamics, okay, would be of the form x2 dot plus bx dot plus kx equals 0. Okay. So no external forces applied here. Okay, just the natural response is what we're interested in. Okay, so we want to understand how the solution behaves. Okay, now this is a very basic, second-order linear differential equation. Most of you, all of you probably have seen this, in the freshman or sophomore differential equations class, right? You take the characteristic polynomial, right? Depending on the roots, solution is going to be either involve cosine sines or exponentials or some combination, right? We can do it that way. Let's do it using matrix exponentials, okay? Since that's what we've been talking about a lot in this class. Okay, so define x1 equals x, x2 equals x dot here. Okay, as I said, we don't have to do it this way, but I thought this would be a good excuse to show you sort of a general, method for using matrix exponentials for solving equations of this form. Okay. All right, so x1 equals x, x2 is defined to be x dot, and then we can rewrite this equation in the form x1 dot, x2 dot is equal to, 0, 1, and this becomes minus k over m, but we assume m is 1. So we'll say this is minus k, and this is positive b times x1, x2. Okay. All right, so, this is a standard linear differential equation of the form x dot equals a times x. Okay, and we talked about this a lot, right? Finding solutions to this. So x of t is e to the at x0. Okay, so here's a convenient way of deriving the solution to that. Okay, so we let lambda 1, lambda 2 be the eigenvalues of A. The eigenvalues of A. Okay. Remember in your freshman or sophomore class, right? You learned that the solution depends on the nature of these eigenvalues, right? Well, it turns out the matrix exponential also depends on the nature of these eigenvalues. Okay, so we can split this up into a couple cases. So first case, if lambda 1, okay, if lambda 1, lambda 2 are both real, okay, and lambda 1 is not equal to lambda 2, that is, they're distinct, okay, then you say that e to the at is of the form some constant m1, it's a constant matrix now, m1 times e to the lambda 1t plus m2 times e to the lambda 2t. Okay, where, as I said, m1, m2 are 2 by 2 constant matrices. Okay, all right. So, so the trick now is to find m1 and m2. And to do that, we need boundary conditions. Okay, so find m1 and m2 using boundary conditions. And we need two of them because we have two unknowns here, m1 and m2. Okay, so what are they? Well, let's see. The first one is, okay, so e to the at, let's evaluate this at t equals 0. Okay, so this should equal m1 e to the lambda 1t plus m2 e to the lambda 2t, all evaluated at t equals 0. So that's m1 e to the lambda 1t plus m2 e to the lambda 2t, okay, at t equals 0. T equals 0. Okay. So straightforwardly, A equals m1 plus m2. Okay. So there's one boundary condition. Second boundary condition, we need something that's independent. So this always works. Take the derivative of both sides. Okay. So take the derivative d dt of e to the at. Okay, take the derivative. Now evaluate this at t equals 0. Same thing, take the derivative of the, yeah, sorry, mistake, this is I here. Okay. Okay, yeah, this, all right. Several typos here being pointed out. Thank you. I think this is also minus b. Yes. Okay, so have this. Take the derivative of the right-hand side. Okay. All right, so let's just write it here. d dt of m1 e to the lambda 1t plus m2 e to the lambda 2t. Okay, evaluate at t equals 0. Okay, and if you do that, you get, let's see, a. Okay, take the derivative of this with respect to t. You get a times e to the at. T equals 0 leaves you with just a. Okay, and right-hand side we have, right, lambda 1 comes down, t equals 0, the exponential becomes 1, so this is lambda 1 m1 plus lambda 2 m2. Okay, so using that and this, we can find m1 and m2. Right? Simple linear equation. All right, so that's the case when lambda 1, lambda 2 are real and distinct. Okay, case 2, okay, if lambda 1 happens to be, let's see, I used alpha here. So if lambda 1 equals, say, alpha plus I beta, it's complex. Okay, then that means lambda 2 has to be alpha minus I beta. Okay, because they always occur in pairs, roots. Okay, then you assume e to the at is of the form the following. It's e to the alpha t times m1 times cosine beta t plus m2 times sine of beta t. Okay, so then assume all right, and then we need two boundary conditions. What are they? Same conditions. Okay, use the same boundary conditions. Okay, so at t equals 0, okay, we have I equals, so t equals 0, this becomes 1, this becomes 0. So I guess I equals m1, right? And then now we take the derivative of both sides. A equals, all right, so this is so you want to take the d dt of this whole thing. E alpha t, m1 cosine beta t plus m2 sine beta t. Okay, evaluated at t equals 0. Okay. And then you get two equations in the two unknowns, m1 and m2, and then you can solve for it. Okay. All right, so last case. Let's go over here. Okay, case 3. So if lambda 1 equals lambda 2, okay, the two eigenvalues are identical, then assume that e to the at equals, all right, so what was the assumption when you, for the second order linear differential equation case that you studied as a freshman or sophomore, right? You have e to the lambda t plus t times e to the lambda t term, right? Same thing here. You have m1 times e to the lambda t. Okay, so let's just call it lambda. Okay, plus m2 times t times e to the lambda t. Okay, assume e to the at to be of this form. Use the same two boundary conditions. Okay, same boundary conditions to get m1 and m2. Okay. All right, I didn't have to do this. The reason I showed you this is because this is a very general method. Okay, you can use this approach to solve. Okay, for any arbitrary linear equation of the form x dot equals ax. Okay, where a is n by n and x is n dimensional. Okay, so find the eigenvalues of a. Okay, and depending on the nature of the eigenvalues, assume e to the at to be of a certain form. Okay. And then use the boundary conditions. So if you need more boundary conditions, what do? You differentiate one more time. Okay. So assume e to the at of the form, say m1 e to the lambda 1t plus m2 e to the lambda 2t. Plus you could have complex pairs, you could have repeated pairs, right? Plus say m3, I don't know, e to the alpha t cosine beta t plus m4 e to the alpha t sine beta t, okay, whatever. N of these terms, right? And then differentiate as many times as necessary, okay, to get your independent boundary conditions. As many times as necessary for boundary conditions. Okay, all right. So, and in fact, this method, will be useful when we look at PID control. Okay, when you want to say prove the stability of PID control, because then there you have a third order differential equation. Okay, so this might be useful there. Okay, so this is kind of an aside. Let's get back to our problem. Okay, so for our problem, so for our problem, okay, the characteristic polynomial, okay, are obtained as the roots of this, okay, the eigenvalues are the roots of the characteristic polynomial, which are s squared minus trace of a times s plus, and this is a general result for 2 by 2 matrices, which happens to be s squared plus, okay, I'm going to put the m back in here. Okay, so we assumed m equals 1, but let me just put it in here. Okay, so the roots are, the eigenvalues, lambda 1 and lambda 2 are s equals minus b over 2m, putting the m back in, plus square root of b squared minus 4 mk over 2m. Okay, so this determines the solution, the form of the solution. Okay. All right. Now we can plot the solution. Okay. So solution trajectories. Okay, so we have that equation. So physically, here's a spring attached to the wall, right? Or was it maybe? I guess, yeah, it was this way, right? So pull it, let go of the spring, okay? And then it's going to do this, right? It's going to do that. Or it could just go really slowly to the equilibrium. Okay? So it could do a number of these things, okay? So 3 cases for the solution trajectories. Okay, so first case, So in the case where b square is greater than 4mk, okay, so think about what these terms mean. So b is, that was the friction. That was in front of the theta dot term, right? So this kind of reflects the friction of the system. Okay, k is the spring constant. Okay, so that means the friction term is dominates, okay, over the spring term. So in this case, what happens is, okay, so here's time t, here's x of t, and let's say you start out at, say, x equals 1. You pull it out, you let go. What's going to happen is it's going to slowly go toward the equilibrium. So it's going to go, okay. So this is the overdamped case. Okay. Now let's look at the other two cases. Okay, so second case, let's now assume the other way. B squared this time is less than 4mk. Okay, so if we draw a graph of this situation, here's time t, here's x of t. Okay, so this is the case when frictional forces are dominated by spring forces. Okay, so the spring is much more powerful compared to the friction. So if I pull it, I let it go, right, it's going to start oscillating, right? Eventually, if there's some friction, eventually it'll die down and go to rest. But it'll do something like, okay. So this is the underdamped case. Underdamped. Is in between these two. When b squared equals 4mk. Okay, so what do you think will happen? So in this case, there's no oscillation. It just slowly goes to equilibrium, x equals 0. In this case, there's oscillation. Okay, so there has to be something that happens going from there to there, right? Right before oscillation begins, what happens? Well, it's going to go to 0 in the, for this system, the fastest possible way, without oscillating. Okay, t, x of t. So this is the, we call it the critically damped case. Critically damped. Okay, and from a control perspective, this is the best outcome. Okay, it's the fastest response. It's where the mass goes to the equilibrium, which is our desired state, as fast as possible without any oscillation. Okay, goes to x equals 0, fastest, without oscillation. All right, so when we're controlling something, we want the response to be fast, right? But we don't want it to go overshooting all over the place. So this is what we want to shoot for. All right, now let's turn it into a control problem. Okay, so now let's now consider external force F applied to the spring. Okay. All right, so F is equal to m x2 dot plus b x dot plus kx. Okay, so we have a force, and suppose there's some motor or actuator that can apply a force to the motor, to the mass. Okay. All right. So it's a control system. This is our control input. Okay. All right. Now, here's the goal. Let's find the force F. Okay. That makes the mass go to 0 as fast as possible without oscillating. Okay. But let's also say that for the same reasons that we discussed at the beginning of the class, right? Unmodeled dynamics, uncertain model parameters, and so on, we want to use feedback control. Okay. All right. So we're going to assume F is of the following form, minus Kp times x minus Kv times, maybe I should use Kd for derivative, yeah, x dot. Okay? And goal, okay, is to make x go to 0. Okay, make x of t go to 0. All right, so this, as I said, this is the PD control. Okay, so note F is a PD control law. Okay, so there's the P, there's the D. So P implies proportional. Okay, it's proportional to x. D is the derivative term. Okay, so k sub d is multiplied by the derivative x dot. Okay. All right. So idea here is we start at x equal to something non-zero. Okay, and we want to apply a force to the mass to make it go to x equals 0. Okay, as fast as possible without overshooting. Okay, like the critically damped case. Okay. But we're going to assume F is to be of this form. Okay, so what we do is we measure x and measure x dot. Okay, all right. So x and x dot are measured. Okay, so we have sensors attached to this mass, which give us measurements of x and x dot. Okay, so so now what we do is we put this F into here. Okay, and let's see what the equations look like. Okay, so all right, so mx2 dot plus bx dot plus kx equals minus kpx minus kd x dot. Combine it, we get mx2 dot plus, let's see, I guess we get a b plus kd x dot plus k plus kp x equals 0, which is exactly the same form, okay, as for the case with no control, okay, but the coefficients are replaced now. Okay, so call this, say, b prime, so call this k prime, and we have the same equations. Okay. So critical damping occurs when b prime B prime squared is equal to 4mk prime squared. 4mk prime. Okay. Okay, so this would be the mass spring damper system.